Hello, good evening, everyone. Today I'm speaking to Dr. Kelvin Kemm, and we're going to speak about the Pebble Bed Modular Reactor. Dr. Kemm is the head of Stratic Global, and the topic of discussion is going to be the HTMR 100 nuclear power reactor. So, Dr. Kemm, welcome.
Thank you very much, Hugo. It's very nice to be here with you.
So, let's sort of dig into the Pebble Bed reactor. It's sort of become a bit of a meme in South Africa that we had a nuclear program and we worked on a Pebble Bed reactor, and then, as I understand it, something stopped the program from going ahead. So can you give us maybe a sort of a brief Reader's Digest history as to what this Pebble Bed reactor is about, and we'll go from that direction?
Well, South Africa is a very large country. You know, when you look at the standard Mercator map projection, it doesn't accurately indicate the size of countries and of Africa for that matter. So South Africa is the same size as the whole of Western Europe added together. For example, I'm right now in Pretoria, the capital of South Africa, and Cape Town, where the nuclear power station Koeberg is situated, is right down at the south of the country. But the distance between Pretoria and Cape Town is the same as Rome to London. People don't appreciate that. South Africa uses coal for far the majority of its electricity production units, but the coal is clustered all in the far northeast of the country. So it's a long way to move coal-generated electricity from beyond Pretoria down to Cape Town. So way back in the 1970s, the government of the day, realizing this, decided that they should build a nuclear power station down at Cape Town. It's the most southerly nuclear power station in the world and the one and only one in Africa. So that power station was built and it went online, the first of two reactors in 1984. It is still going strong now and is delivering South Africa's cheapest electricity. As time went by, and the economy grew and electricity demand increased and so on. At the end of the last century, planners sat down and said, right, now what? And as you well know, South Africa has large gold mines inland and other mines and so on. So the question was, how do we continue to supply like the mining areas and some of the big industrial areas which are far inland? And note that South Africa has extremely little water. We're not a country with loads of inland water. We have two oceans on the two coastlines, the Indian Ocean and the Atlantic, but not much inland water. So the question was how to produce electricity inland with no cooling water. And the conclusion that was arrived at was we should have a nuclear reactor, but that nuclear reactor cannot be water cooled. So with some thinking about it, and I was involved in those very early days, they came to the conclusion we better design and build something that doesn't use water. And so the idea of using a small modular reactor came about. At that stage, small modular reactor ideas were embryonic, and we picked up ideas from around the world and decided to pursue the Pebble Bed line. And from the beginning, the decision was to make a commercial reactor, not just an experimental demo type of reactor. So South Africa became the first country in the world to start designing a commercial small modular reactor. And that started in the 1990s. And as we went into the 2000s, this grew very quickly, very large. And amazingly, the total number of people involved, staff involved in this project grew to 2,000. It was the biggest reactor design project in the world by far. And it went very far, to the point at which around 2008 rather to 2010, in that period, the pressure vessel was ordered from Japan and it arrived in South Africa. And then a number of things happened. In 2008 was now the notorious subprime mortgage financial drama that occurred in the United States, leading to a worldwide financial upset at the time. At that stage, South Africa got hold of various large American banks to come and back the project. Interestingly, at the time, we didn't need the money. We had all the money to go ahead. What we needed was the names of those banks associated with the project to give it potential international customers and credibility. As that American subprime thing occurred, the banks were collapsing and pulling out, so all our financial credibility in terms of the international linkages there started to disappear. Then, not long after that, the sitting president of the time, Thabo Mbeki, who was very much a supporter of the Pebble Bed, he was unseated by President Jacob Zuma, who came in and put a lot of large projects on hold pending further decisions. And there were a couple of other things that just by bad luck sort of converged during that period. And the reactor was put on hold. And everybody at the time thought the hold would last a couple of months or so, but in fact, the hold has lasted ever since then until now. So the project was theoretically never stopped. In fact, there's still a Pebble Bed group housed in Nexa, which sits there maintaining the legal entity and the paperwork and a lot of things like that. It's about a dozen people. But it was never rejuvenated as a technological project at the time. So unfortunately, that world-leading status that we had there started to cool off during the next decade or so, while there was still a lot of anti-nuclear sentiment around the world coming from the extreme Greens and so
on. Okay, well, that's an interesting history, and thank you for spelling the facts out of there. So, sort of I want to ask on the principles of the Pebble Bed. It runs on thorium, it's helium cooled. Can you maybe explain to us why thorium is such an important alternative to uranium?
Well, Hugo, it runs on uranium or thorium or both. It was designed to be very versatile. So fuel was actually made here in Pretoria with the understanding that you could make it with either entirely uranium or thorium or a mixture. And this was done for experimental purposes. Now, of course, uranium, when uranium splits, it produces quite radioactive daughter products, they called in nuclear physics. In other words, the waste or the spent fuel is quite radioactive. In the case of thorium, the residue from a thorium reaction is a lot less radioactive. There's also a lot more thorium around the world in lesser concentrations, more widely spread. In fact, the richest thorium mine in the world is in South Africa in the Western Cape province. It was responsible for generating fuel for some of the earliest ever American reactors and British reactors. They were fueled by thorium from South Africa. But then historically what happened is that it was recognized that uranium was far better for weapons production. So during the Cold War era, a lot more research was put into using uranium, and I think that was the main reason why thorium was put aside during that period. But thorium is much more widely spread around the world. It's also, from a proliferation, meaning anti-weapons point of view, it is much safer, it makes people more comfortable. So we said, okay, let's put thorium into the mix as well, so that we can satisfy people that will be upset potentially about possible weapons proliferation. Also, we can tell all sorts of countries you can get into the nuclear business because you're not dependent on only one or two suppliers for uranium. That why it was to include thorium in the mix. Currently, what we're doing, though, is we're concentrating on uranium because there's so much more history in uranium. And our first reactor that we're building now, we would fuel with uranium fuel, but certainly thorium fuel can be done if somebody wants to do it. It's all there waiting to be exploited.
Okay, so finishing this Pebble Bed is not it's not dependent on a thorium fuel cycle being established. You make the argument it runs on uranium as well.
Absolutely. In fact, fuel was manufactured in Pretoria. A small plant was built. That current small plant stands today in a care and maintenance state. It's ready to reactivate, which we can reactivate in a few months and get going again. Now, I'm sure you're getting to this question, so I'm going to preempt you and jump in anyway. But what happened as this hold on the Pebble Bed reactor just went on and on and on for the next couple of years, the scientists and engineers who thought it was going to be resurrected realized that this wasn't likely to happen soon. So they got together as a private grouping and said, right, let's go ahead and develop our own version of this, which is what happened. And then a variant reactor was developed from that called the HTMR 100, 100 representing 100 megawatts power. So they looked at the first reactor and said, all right, it had government money, it had international support and so on at its height. We're now a small group. They asked around for private money. Of the order of 50 people came along and put money in. So there was enough money to go for a number of years. In fact, it ran for about a decade in development in that format. And so they looked at it and said, right, now what? And then two important decisions were made, technological decisions. The Pebble Bed reactor is cooled with helium, but the helium came out of the reactor at a temperature of 940 Celsius. That helium then went straight into a turbine, which is thermodynamically the best way to do it. And then from the turbine back into the reactor to be reheated. But that meant that there was the complexity of designing the turbine system and circuit as well. So with the HTML 100, they made the decision to reduce the exit temperature from 940 to 750, which is still very hot, and to not put the helium through the turbine, but to put it into a conventional water heat exchanger, which would produce conventional steam. So that was done. So the design that has evolved from that now goes into a conventional heat exchanger, which is in the business known as the steam generator, because out of it now comes the high pressure steam, which goes into a conventional steam turbine. So everything from there downwards, so to speak, is off-the-shelf equipment that any potential customer can phone anybody in the world and buy the turbines and the generators and all the other power station gear that goes down line. So we developed the reactor and then that interface with the water heat exchanger. And so that made it much cheaper to design. It is faster to build, and therefore is from a commercial point of view, a much more saleable first product. And that's where we stand today.
So theoretically speaking, somebody can take one of these reactors and you can replace an existing, small power plant, because it's a small modular reactor, and just sort of plug it in. And that would, obviously with some modifications, I assume, because, things never really fit as it should. But theoretically, that's possible.
Yes, that has been discussed by a number of people, that there are, for example, coal-fired power stations around the world. And in numbers of cases, the coal-fired power stations are being wound down. But what they have, of course, is all the switchyard, and they have generators and so on. So in principle, yes, you can take one of these reactors and put it at the site of a coal-fired power station, put it into a heat exchanger, then take that steam maybe into the existing steam turbine or into something there, into existing generators. So there's quite a bit of talk of refitting a coal-fired power station to run on a small reactor. And of course, as I mentioned, the small reactor was designed to not use water cooling. So you don't have to be next to the ocean or next to a massive dam or water source of any sort. So you can put this wherever you like. And that opens up many other possibilities from a design and logistics point of view as well.
Okay, well, that's interesting because, as you say, water is a big issue throughout Africa, for example, and we have these mines in the middle of nowhere. And I would assume that you were targeting those type of customers as well.
Yes. No, well, you mentioned water in Africa. That is terribly important, and that was taken into account in the design phase. If you look at a country like Norway, Norway has a lot of hydro. But then I've been to Sweden, I've been to Finland, I've been to Denmark, I've never been to Norway. But in Norway, the dams tend to be in geology that looks like that, so fjords or something. So you make a dam and there's always water runoff. There's ice and snow, and that's the vision the one gets is these Norwegian hydro plants are always full. And the physics of it is the height of the water, and then the volume of the water is what gives you your pressure and your throughput, so that you've got a guaranteed electricity output. In contrast, African dams look like saucers. They look like this. And they're very big in surface area, but not that deep. Right now, there's been in the news around this part of the world that Lake Kariba, the Kariba hydro scheme in Zimbabwe, is down to an extremely low level, so low that the hydro out of that is almost not occurring at all. It's down to something like 10% output. Because here, any drought conditions for a while or any substantial loss of water, like from excessive use of the water or dry conditions causing evaporation and so on, you lose a bit of the height of the water and you've lost a huge amount of the pressure which drives the turbines. And with that big saucer-shaped surface area, no guaranteed runoff like ice and snow, and that you can't rely on the hydro either. Not like Norway that exports hydropower to the UK via undersea cables. So even relying on something like hydro in Africa is not a long-term solution. Even an interim solution is not reliable. So in other African countries, they need something that they can put anywhere they like and is not water dependent. And a gas-cooled
I think I've lost your connection for a while over there. I'm not sure, there's a delay. Just give him some time, and please, guys, let me know if you've got questions. It's unfortunately internet connection. I hope it's not load shedding in South Africa. Well, they desperately need Pebble Beds if that's the case. But we'll just give him a few minutes. Yeah, so he is disconnected. I see there's only 7 of you watching live, but yeah, thanks for doing so. Just give him a few more minutes to come back. And let's hope that that it's not Eskom. I suppose if you have questions for me, you can ask them in the chat as well. Yeah, so I've sent him a message and I haven't got a response yet, so I'll give it like 10 minutes, 5 to 10 minutes, and let's see, something went wrong with the broadcast. But thanks for listening to the first few minutes. You're asking Knox about how true is it that the Chinese stole the technology? Well, I've heard that story as well, so I would like to ask him about it. But I know that there was some agreement. I think it was University of Johannesburg or something that worked with them. So we'll have to find out. It's a very, very good question. But don't stress to whoever's listening if this issue persists. We just do another talk maybe at another date. I mean, Dr. Kemm is always willing to talk, so it's one of those things. I suspect it's Eskom. I don't see any response from his side. Eskom or internet. Don't know if anyone can see if that area of Pretoria has load shedding. And I must say, it feels kind of strange sitting in front of the camera speaking alone to people. I'm asking you, should SA stick to something safe like pressure water reactors, or the risk of pebble beds worth it? Well, my understanding is pebble beds have got fewer risks associated with them, actually. Just to explain that, pressure water reactors are risky by their nature because you're heating up steam as your coolant, or water as your coolant. So you're making steam that can easily go into hydrogen. And that's why there's a risk of explosion during earthquakes and things of that sort. It's actually not the radiation that's the risk, it's the steam. that can go into hydrogen. So with Pebble Bed, you don't have that issue. So it is something worth pursuing. The question is the product ready for launch and economically feasible? That's always been the question. But in terms of design safety, it's a much safer design. You say the problem of Kariba is insufficient catchment upstream. Yeah, it might be, but that would be then a case that if that's the case, it means that Zimbabwe is running out of water, because the general rule is, I think, you can only use up to 60% of your river water in dams. If you start exceeding that, you start having these type of issues. So it might be that Zimbabwe is drawing too much water from the dam; they're running out of water, which means desalination, trade agreements, stuff of that sort, or just building more dams. I mean, I'm assuming the Zambezi is not that dry.
You're muted.
Now I'm back. Welcome back. Was that ESCOM?
No, that was unfortunately my wife today. I went out and I've got the Wi-Fi hasn't been moved over. It was supposed to come over yesterday, so I'm actually driving through an old cell phone connecting that way, and the cell phone was on permanent charge, and somebody pulled the plug out of the wall, so the cell phone was running on its battery, and suddenly the battery gave out. So then I dashed and discovered that the charger had been unplugged.
Okay, well, so ESCOM doesn't get the blame for that one. We've got some questions for you while you were away, and somebody's asked this clever question. We asked, should South Africa stick to something safe like pressure water reactors, or are the risks of the Pebble Bed worth it? And maybe explain the safety features.
Okay, well, firstly, I think one must point out that the large reactors like the pressurized water reactors, I believe we should go ahead and do them as well. So the plan is still to build something like 3,000, 3,500 megawatt large reactors. Pebble Bed types are much smaller, like 5% of the size at 100, 200, 300. The International Atomic Energy Agency defines small reactors as 300 or less, in fact, 100 to 300 or so, and below that even micro reactors, which we're working on one of those here in Pretoria as well. So I believe we should do both. The larger pressurized water reactors are great on the coastline. Currently, South Africa has got 5 new sites identified for larger reactors. They've been identified years ago already, and I believe we should go ahead and use those for large reactors. But it's inland, far away from the water. Inland, we're talking about 500-600 kilometers away from the oceans. That's where we want to build the small modular reactors. And we know what we're doing. We were the first country in the world to go into a commercial design. We don't believe there's any risk in the sense of a financial risk now. We know what we're doing. We've done it. There's no more risk in doing this than there is in any other comparable type of energy production. So I think it's a worthwhile bet all round to do both of them.
But do you think, I mean, I'm going to ask you to speculate a little bit here, but here in France, where I'm sitting in the I think it was the 70s, under de Gaulle, they had a prime minister, well, I think a president prime minister by the name of Pierre Mesmer. And he made the Mesmer plan, which was to basically put France on a nuclear, foothold. Don't you think South Africa should maybe, now that we're in a crisis, look into something like that? It's a long-term solution.
Well, I think what is necessary is for politicians and business leaders to make courageous decisions. And if you look in the past and say, what great things happened, I believe that under so many of those politicians or certain business leaders, they had to make courageous decisions. And many of those big decisions, you cannot have the facts at your disposal, all of the facts. There's no ways you can have a really large decision like to build a new harbor or to do something like that and have everything correct. You can have a good shot at it. And I can remember, for example, when South Africa built Richards Bay Harbor. Richards Bay Harbor at the time was a river estuary with birds and crocodiles, and that was it. There was nothing there except a little village. And that is, shall we build a harbor? That was the biggest harbor ever built in the world, one shot from a single plant, so to speak. And there was much debate as to whether this was a good idea or not. And if anything, the majority of people said, no, that's not a good idea. It's far too big a thing to do. And somebody's got to say, it feels right, it looks right into the future, let's do it. And many times you find those are the sort of things that when people pushed for the oil industry and Henry Ford built the motor cars on a commercial scale and so on, they just say, it's going to work, let's do it. So I feel now that we've got to make a decision that this is the right thing to do, and then get private enterprise together, because all of these reactors are always built by private enterprise. It might be the government or government-linked entities that are the overall project managers and the warders of the projects, but the concrete is poured and the steel is welded and all that, all by private firms working together. So, I feel that is what's necessary. And obviously what counts against that often is the propaganda propagated by the extreme greens. I watched an interview that you did a while ago with Andy May, where I was quite stunned to see the magnitude of what Greenpeace has been doing with their, quite bluntly, dishonesty and manipulation to make money. It's a money-making organization. And I've since spoken to a Greenpeace leader in somebody who knows a Greenpeace leader in Amsterdam. Face to face, I spoke to. He says, this chap there says he knows what he's doing is quite dishonest, but he's well paid. And he sits out of the limelight and he just creates all the propaganda, gets well paid for it, knowing it's wrong, but it's an easy job and he gets lots of money. And sadly, that's a lot of what's happening. So, we need courageous leaders now to say, right, let's do it. And you can't sit and wait for the scientists and economists and whatever to absolutely prove down to the last fraction of a dollar or something that this thing has got everything in the right place. You just never get that resolution in a big project.
No, you can't. And I mean, having worked on similar projects, things. You pilot stuff and you see what works, and you fix the errors and you go along, and that's how you get there. I've got another question for you. Somebody asked here. Last year the Chinese started that Pebble Bed. They say, did they steal our technology? What went wrong there?
We were right with the Pebble Bed technology. It's excellent. A number of other people then looked at it and we gave them confidence. I know, for example, that we worked a lot as well on all the rules and regulations and procedure and that at the time of Generation 4 reactors. And now I've heard from a number of people, you go to any Generation 4 nuclear conference anywhere in the world, and you can't get through a Generation 4 conference without people referring to all the South African baseline that was laid down and the South African procedures that were designed and developed and so on. And so, all of that is in place. And many people obviously looked at what we put into place and followed the same procedures. And also, the origins of some of the science. And so I think there are a number of people that are following the Pebble type path. But by the same token, there are a lot of others. There's molten salt, there's molten lead, there's all sorts of variants that are being tried. And that is the nature of the game when a new era opens up. When motor cars, the Henry Ford, Model T Ford time, numbers of other people tried to get in on the market and said, let's try this and this and this variant. And so there will be various variants. And I think eventually 2 or 3 or 4 or something might come out of the mix that are particularly applicable, like in the case of nuclear warships, nuclear submarines, and so on. A lead-cooled reactor works because you've got somebody there all of the time watching it. You can't have a lead-cooled reactor where you allow the lead to freeze. That's not good news at all. So there's some that will be particularly applicable, but I think for our design and our conditions, a helium-cooled graphite ball containing uranium or thorium is the right answer.
I'm going to ask you on the helium. You obviously, you mentioned before that water is scarce in Africa and helium is a logical conclusion. How easy is it to get helium and what does the helium supply chain look like?
I don't believe it's too difficult to get helium, but interestingly, now that you ask, some people in the Free State province of South Africa have just discovered that they're sitting on top of one of the biggest helium supplies in the world. And I was reading about it recently, and this company went along and bought the mineral rights for some piece of land some years ago now, and apparently paid $1 or something like that for the mineral rights, and have now discovered that they're sitting on top of one of the biggest helium supplies in the world. So right now they're working towards exploiting that, and they're talking about becoming one of the biggest helium suppliers in the world. So I've never been aware of helium being a problem. Obviously, if many reactors come about, the supply and demand reality comes into play. But I can't see helium supply being a problem. Of course, it stays within the reactor. It's not consumed. So once it's filled up, it's filled up. There will be leakages and so on. So you need to top up from time to time. But it's not as if you're using a vast amount of helium on a continuous filling basis or something. So I can't see it's going to be a big problem.
So you're saying because I mean helium is the second largest element or second smallest element on the periodic table.
Yes.
So you're saying there's obviously a little bit of heat leakage loss, but it's the technical issues around that has been solved.
Yes, certainly when we've done experimental developments, and it hasn't presented any problems. But as you very correctly say, things like the day-to-day problems when you do an engineering system of somebody joins up two pipes and at the seal there's a leak at the seal and so on. When you do it in the laboratory, you make sure you're absolutely right. But you've got to take into account the day-to-day reality of running a plant like a nuclear plant. But saying what you said brings me to another thing which I think is important. Now, the nuclear power business, from its inception, has had exceedingly stringent rules applied to it. I think very unfairly most of the time, but in fact, it's put us in a good place. Let's face it, the nuclear power birth to the planet was the worst one you could imagine. It was dropping 2 nuclear weapons on Japan. That's what brought nuclear to the attention of the world. And after they did that, somebody said, you know what, we can take these things and make peaceful nuclear power packs out of them. And everybody said, whoa, you can imagine. And the anti-nuclear lobby in the early days, which tended to be the anti-nuclear weapons lobby, played that up a lot, saying, you can't put a nuclear bomb and a reactor will blow up and so on. Now, nuclear reactors cannot blow up like bombs. They just don't have the configuration out there to allow for that. But that wasn't known for throughout the 50s, 60s, and probably and even now, probably many people still think it can. So what came out of that is that nuclear was policed in an incredible way. You go into a nuclear reactor, you can't just walk, there are doorways, you can't just open and close the door. You've got to sort of be signed in and out of the door, and there's airlocks, and you can't go through that door if that door is still open and so on. So they are super careful with what goes on inside a nuclear plant. And it's when you have very good housekeeping like that, it's much easier to keep your very good housekeeping in place than to try and improve it later. So I think it's good that we have those excessive, if anything, rules and regulations in place, because then when somebody joins up a flange, they will join up the flange correctly. So it won't be like somebody just knocking together water pipes at the municipal level that if the pipe leaks a bit, so what type of thing. And as long as you abide by the nuclear rules and procedure and make sure everything's done correctly, I can't foresee that that's going to be major problems. They've all been detected up until now and have been taken into account. So, as with any engineering project, you're going to go from your prototype to the larger working model, but that's in the nature of any game.
In terms of the helium, like say theoretically speaking, there's an earthquake and there's a loss of coolant accident like Fukushima. In a pressure water reactor, it's always actually the hydrogen gas that can explode. That's usually the big risk there. It's not that much radiation as some people would think. But what would theoretically happen then in this Pebble Bed reactor?
All right, that's very interesting. If you look at energy sources like wind and solar, there's a lot that I've seen of people emphasizing how technologically advanced the wind and solar is. And that's very true. When I look at a wind turbine, I can see the beauty of the blades, and I know the physics that went into the curvature of those blades and the bearings that are inside those big machines and so on and so forth. And similarly for solar, a lot of technological advancement has taken place. But so has it taken place in nuclear. And I find people saying, look at all the technological advance taking place in wind turbines, and they assume that nuclear power stopped in the 1970s. It didn't. The nuclear power has continued. And any technological advance goes hand in hand with sociological advance. the advance of the law, and so on and so forth. And over the years, what happened is that people said, oh, when we did the first nuclear reactors, we built them to be good at producing electricity and heat, but there wasn't the psychological attitude that there is now towards things like the fear factor of the public and a potential radiation release. So what has happened is the concept of passive safety has come about. And that means you use the laws of physics, so when things go wrong, the laws of physics work in your favor and tend to close things down, and not like Fukushima, where the laws of physics were such that they made certain things worse. Like Fukushima had a used fuel storage such that the water was higher up and therefore gravitationally would leak out. So they had to worry about how to put water in this when it got cracked and water started to run out. Chernobyl is the example of this. That Chernobyl was designed to produce good heat, which it did. But as a result of designing it that way, the reactor had a runaway effect when things went wrong. And the reactor started to run away, overheating itself, and you know what happened. So now the psychological concepts when you start is the passive safety, that if everything goes wrong. Now, in the case of the Pebble Bed, it was designed such that we always said, if the worst of the worst happened, the best thing everybody can do is go down the road to the closest pub and sit there and have a beer and sit and think about it. Because the Pebble Bed was designed that it would rise up to a maximum temperature of 1600 C, and then it would sit there for a day or two and then gently cool itself off over the next 5 or 6 days down to nothing. So even if the worst happened and all the coolant leaked out and everything went absolutely wrong, the reactor would just get a bit hot, sit there and cool itself off. The reactor is designed to take temperatures of 2000, so nothing's going to melt, and the maximum it'll get to is 1600. And so that's that, and that has been put into it. And there's numbers of other passive safety, such that if something happens, control rods fall down under gravity to shut the reactor down, and things fall down and go in, and all that type of thing. And I'm trying to speak in a very layman's language here, but everything that's possible has been designed in that the natural laws of physics will work in your favor from a safety point of view. So a Pebble Bed reactor is exceedingly safe.
Okay, and you don't, the passive safety obviously allows us to get away with all the active safety features. You don't need policing of the thing or something, you know, they employ 10 people watching the reaction all the time, something of that sort.
No, there will be people watching it very carefully. But yes, you're right. You wouldn't have to watch it quite as carefully. But now, of course, when I said about the advance of technology, a project that I was involved in a couple of years ago was to monitor and control machinery via the internet. We did some experiments on that. And I was personally involved in some experiments where we were sitting in Johannesburg and we switched pumps and various other machines on and off. Some of the pumps were in Johannesburg, somewhere in Australia, and somewhere in a European country. And we sat there switching them on and off and measuring things like RPM and temperatures from Johannesburg to prove that you didn't even essentially need humans in Australia and you could switch those machines. Now, I've got a bit of a dream where I imagine that we could have 20 or 30 Pebble Bed reactors, for example, around Africa, all linked into a central, I hesitate to say control room, monitoring room, because now the politics comes in if you say control room, but we could have a monitoring room in Pretoria, for argument's sake. On the screens, you could see the temperatures in all the reactors, you could see pressures, you could see flow. Watch this. So you could have like an air traffic control system. You have an air traffic controller, set of air traffic controllers watching a whole lot of airplanes in the sky, warning all the airplanes whether they're in the right place or wrong, if there's a storm coming and so on. So you could have some central grouping that watches and then picks up the phone and calls Zambia or Kenya or the DRC or something and says, by the way, we noticed that your reactor number 3 has got a rising temperature and so and so. We recommend you go and have a closer look and let us know. And you can do that without any wires connected. It can all be done via the internet. The reactors could be in South America. They could be in Russia. They could be in Iceland or something. And you could do the same thing. So the opportunities for having this sort of advanced control and monitoring are much greater than they were a few years ago. And of course, AI, robotic intelligence, all that type of thing will make it much easier to control, even tighter, but without the humans having to be there all the time.
Yeah, and I mean, modern structures, just from a structural point of view, have got they're now looking at fiber optics or sensors, active, strain gauges that measure real-time strain. So, if there's a
Yes.
crack formation, you can pick it up very quickly. Things of that sort. I've got a question for you on the fuel. Can you maybe explain how this works, what those balls are, and how the refueling theoretically would work?
Oh, all right. In the case of the HTMR 100, they have a once through, then out. It's called OTTO, OTTO fuel. So the fuel ball goes in at the top. There's essentially a big tank of balls. The balls are about the size of a cricket ball. And those people who don't know what a cricket ball looks like, it's slightly smaller than a baseball in America. But a cricket ball, 60 centimeters, 60 millimeters across, 6 centimeters. And that is a graphite matrix. And in that graphite matrix, there's about 9 grams of uranium, enriched to 10% approximately. And that uranium is about the size of grains of sugar. And each one is coated in a number of layers, but a layer of graphite and then silicon carbide, and then another couple of layers. The making of that is a very high-tech business, and that's the development is done here in Pretoria. And that now is very important because it leads to its own safety in the sense that every one of those grains of uranium has a silicon carbide shell around it. And that silicon carbide shell is its own containment vessel. So each one of those grains, if something radioactive comes out of it, a fragment, it is stopped by the silicon carbide wall. So you're not even relying on the outer pressure vessel, which is the case with the conventional PWRs to be your sort of barrier between the uranium and the outside world. Each of these silicon carbide little shells is a containment. And the various other layers are allowed for expansion and distortion with radiation and so on. And then that is all rolled together like a chocolate chip cookie. And then there's an outer layer of graphite put onto it again. And it's very solid. I've stood with somebody who took one of these and hurled it against a concrete wall, and it sort of bounced. Now, it's not as if you even take one of these and throw it against a concrete wall, it'll shatter. But even if it did break, it doesn't matter. It's like taking a bread roll and breaking it in half. It's not like an egg where there's something inside that'll run out. So it doesn't matter. But in fact, they don't break because they're very tough. So they go in and they spend 1.5, 2 years or something in the reactors. They slowly work their way through, and then they are brought out at the bottom. So in principle, you never have to switch the reactor off. It just runs continuously. The only time you switch the reactor off is when some human manager decides that you're going to do it for a maintenance reason or whatever the case might be. But there's not a necessary switch off for a refuel or something like that.
And what is the gain in when you don't switch off the reactor? Because I mean, nuclear reactors normally run at, I think, 90% capacity, and that 10% is the on and off for maintenance. What can you theoretically get through the Pebble Bed?
Well, you're talking better than 90, and as you correctly say, it's things like maintenance and so on. Whatever your operating protocol is when you build one, what you decide. Generally, you wouldn't ever have only one reactor. You would build a power station with 2 at the very least, preferably 3. And then you'd have some maintenance system where if you've got 3 reactors, one is taken out of service every alternate year or something for a checkup. So that's what you would do. And but that is very important. And also now with the fuel, something that is very important, of course, with nuclear fuel generally, is that you use so incredibly little of it. I mean, if we look now what's going on in Europe with all the energy security issues and so on, the panic is where's the gas coming from and where's the coal is being brought. South Africa is exporting coal like crazy at the moment to Europe. Yeah. It's gone up like 5 or 6-fold as the exports from South Africa of coal is pouring out of the country. It's that supply line which is the big worry. I did a calculation a while ago that Coburg, which is about a 2,000 megawatt power station, if Coburg were coal-fired, it would use 6 train loads of coal every day. This is running continuously. And but since it's nuclear, it uses 1 truckload of nuclear fuel per annum, 1 truck a year. So you can bring 3 smaller trucks and they can arrive every 3 or 4 months or whatever you like. And if it's a rainy day, you can decide not to go today, you go tomorrow. and so on. There's not like a conveyor belt of coal or a pipeline of gas that has got to run 24 hours a day all of the time. Now, obviously, if you've built yourself a small modular reactor in Zambia, a couple of 100 kilometers away from a city where a mining area is, or one in the middle of Uganda or something like that, your ability to bring fuel in when it's suitable is terrific, because you don't have to have a pipeline running all day, every day on a 24 hours a day delivery. And that's terribly important. And that was something that we very much took into account in the early days. And why now I think a lot of journalists and a lot of people around the world are waking up rapidly to the fact that nuclear is the future.
Yeah, that is the one reason is the dispatchability. You say fuel can move easily. And the other issue is the materials demand. I mean, it's been ridiculous that people thought you can have these massive supply chains and there's going to be no issues associated with them. Someone else is asking you a question here on X Energy in the United States. He's heard that there's a lot of South Africans working on there. What do you think about their design? That's also Pebble Bed, to my understanding.
Yes, it is also a Pebble Bed. I don't know absolutely all the details of it. What I know about it, I've picked up through reading a few documents and a few things like that. I've never had the privilege of visiting them. But certainly there are a number of South Africans on the X Energy project that were part of the Pebble Bed project here. So they obviously went with the experience of what they'd learned here. And with, I think, the philosophical decisions that it was a good way to go. And so I think they're doing well from what I hear. I think that from my perspective, I think we can do better here. I think we can have a reactor running before them. We, of course, have the advantage of the 25 years worth of research and development work that went in. That's still all here. When they left, they obviously didn't go with 25 years of research and development. They went with a relatively small percentage of that. And then they had to start from cold start in the United States. They've got some money, but we need to get quite a bit more now. And it's a case of there being the psychological decisions to go for it. And then people join in, whether they are government agencies or private enterprise.
How would let's talk a little bit about the financing and stuff. I guess people would ask, like, how, if I theoretically have a lot of money and unfortunately I don't, and I'm interested in this, where do I put my money down, and how do you get it kickstarted?
Well, we've had quite a few people from around the world calling us interested in funding us. This has been going on for a year now. And at the beginning of 2022, we had people phoning up and saying, we hear that you've got a good idea. And we said, yes. And we were having discussions with them. This has gone ahead quite a bit. Somewhat before Christmas, we had a visitor that came from Washington, D.C. and had face-to-face discussions with us and is very interested. We're having continued interaction there. We've had last week a visitor from London, face-to-face again, saying that he'll be back probably in February to go into further detailed discussions. We've had people from Mauritius come here twice, reporting back to the Prime Minister in Mauritius to say, look, this is a good idea. I personally saw the Prime Minister of Mauritius myself and had dinner with him. And he said, look, this is the type of thing we need there. So you can see it's applicable for an island country like Mauritius or a large country. I've had video call meetings with a couple of people that were cabinet members of the previous government in Australia. They have got a pro-nuclear group going in Australia. Currently, Australia is not going nuclear power according to legislation, but there's a number of people there that feel that this will change soon and they are pushing for it. They've shown interest. There are a number of other countries that are showing interest. And certainly in the past half year, there's been significant acceleration. We found a large number of newspaper articles coming out around the world where people are saying, look, the answer now is nuclear. Now, I personally believe that eventually coal will go away by itself because it'll be a natural progression. You see these pictures of London in late 1800s or something where there's horse-drawn carriages and motor cars going down the road at the same time. You can see pictures of a sailing ship, wooden sailing ship sailing out of harbor while a steam-driven boat is coming in. they were overlapping. And then as it showed that the petrol engine was better than horses, the horses just naturally gave way. The sailing ships naturally gave way to steam when steam showed it was better. I think we're in that position now that nuclear over the next few decades is going to just plain and simply prove itself to be far superior to coal. So coal is just too entrenched now to get rid of it overnight. Coal is used all over the world. But I believe nuclear will come about in all different sizes, from micro reactors through to the small modular reactors that we're talking about now, to bigger reactors and so on. So in years to come, there will be reactors all over the place doing a variety of jobs, from large-scale grid supply down to dedicated running one gold mine or running one factory or whatever the case might be. And we're in that transition period. And those politicians and business leaders who can see the future and have got the courage to do something about it will be on the bandwagon like Henry Ford was when he realized that cars weren't just a plaything. Because at that time, I've read that when Henry Ford was making motor cars at the beginning, people were looking upon motor cars as the thing that wealthy people used over weekends for fun, but no serious person used them for business or anything like that. And it took a few years for people to say, no, these things actually can be used much more than just weekend fun for the wealthier people.
Yeah.
And that's where nuclear is now.
A question for you on using pebble beds or for industrial heat, I guess is the question asked. People are talking about decarbonization of, I know we're not going to go into that debate, but I mean, is it possible to use this for industrial heat, and is that process more efficient than, I think, natural gas, which is still the dominant, player?
Yes, actually, that's a very good point that has been raised there. That when the earlier days of the Pebble Bed were going along and there was the focus on electricity, at some point somebody said, we can use process heat, because I remember it striking me forcibly. We just say, what do people do with electricity? And if you go and look at factories and so on, so much electricity is used for heating. People use it to heat all sorts of things. And you say, why make electricity to use electricity to go back into heat? Why not just take the heat straight away? And we started to do some of the financial calculations, and it seemed to turn out that it was more profitable to skip out the electricity and just use the process heat in many cases. You can build a reactor, and we sort of had a vision of a pipeline going out of the reactor with a temperature of 750. You take it around a circuit, and the first people use it to melt tin or something like that, which is used in the making of hacksaw blades or so. And it goes around, and eventually at the end of the circuit, people are molding plastic buckets and so on, where you use low temperature heat and then back into some system with a reactor. So certainly all sorts of options like that of process heat, either going around in the circuit of temperature going down, or just straight into something that is using the temperature at 700-ish or something. There definitely is a lot of opportunity. In fact, in the earlier days of Pebble Bed, I had a few phone calls from the Canadians at the time, and they were very interested in getting the tar out of the iced up areas. And I'd heard then that there were these tar sands in Canada, but they were all frozen into the ground. And the people phoned and said, look, we know all that oil is down there and it's frozen into the tar sands. What about we drill a hole down and we push this hot gas or hot water or something down the hole, melt all the tar sands at the bottom, and then bring up a mixture of water and oil and something on the other side? Would the Pebble Bed reactor do that? And I recall at the time saying, yeah, it would be terrific for that. And we, for over a year, we were dealing with these people on that as a distinct possibility, which is exactly what I think can be done. And in fact, right now, Canada is one of the countries that's very interested in small modular reactors. And also, particularly, yeah.
I would guess industrial cooling as well. I mean, a fridge, as you know better than me, that you've got a hot side and a cold side, and it's basically, the fluid being compressed. That should also work.
Absolutely. Well, this whole modular concept now, what has come out of that is you should try and build all the components pretty small so that you can carry them around on a truck, for example. So the idea being that you build the reactors indoors. And there's a couple of motor car plants in Pretoria that I visit every so often for various reasons. The world's second ever BMW plant was built in Pretoria, by the way, the first one in Bavaria and the second one in Pretoria. There's a large Ford plant in Pretoria as well, making Fords that are exported around the world. And when I first went to those plants, I remember looking at the measurement, how they measure the chassis and it goes down the line. And over the years, I've watched them evolve. And so now there's laser beams bouncing off and computers measuring the laser beams. And, in the early days, I thought the chassis were measured extremely accurately before they went on down the production line. Now, with laser beams bouncing off them, there's computers and robots, and the humans tend to stand and watch this while it's all okayed down the line. So you get huge precision if you can build indoors with robotics and lasers and so on. So the plan is that the modular reactors can largely be built indoors in pieces, that these very accurate pieces then go out, any one of which could go on a truck, and then you carry it to site and you put it together like Lego bricks and bolt it all together, do some welding on site, but that you're not really fabricating assemblies from scratch on site. That makes it much easier to put it together in remote places and much quicker to put it together in wherever you choose.
Well, so the entire construction industry is going that route, yes. Anyways. Everything is modular these days. I want to see another question here. So the Pebble Bed, the critique against small modular reactors has been that, well, show me one, show me one that works, and then I put my money down. Is basically what the investors would say. Like, well, how do you respond to that?
We've had a lot of that, particularly being South Africans, and I visited another small modular reactor developer in the UK, and at the time, those people said to me, "You South Africans are way ahead of us." But what made me a bit jealous was if they make an announcement of something they're going to do, it's splashed in the newspapers. They go to do so and everybody just assumes that they're going to because they're British with a name. Us coming from South Africa, when we say we can build a nuclear reactor, you find people saying, "Really?" So we've had to convince people that we know what we're doing. But to try and answer your question another way, there was the Wright brothers built the first aeroplane. There was somebody built the first this, somebody had to have confidence at some stage. Now we're far better off than they were. That we don't have to actually build an operating one. These days, with advanced computer simulation and your ability to make sub-assemblies, you can show all the pieces with a much greater degree of reliability than the first people to make early aeroplanes and cars and all sorts of things, many of which developed all sorts of terrible problems after a while. So, I've got every confidence that it'll work, that there's no doubt about that. And I mean, you have a look at something like the Boeing 787, for example, the Dreamliner. I read that there was something like 200 faults that were found on the Boeing after it went into service. The most visible one was that incident where it took off one day with a whole lot of passengers on board and smoke started to come into the cabin. Something went wrong with some battery. And the pilot had to say, "Don't worry, folks, we're going to make an emergency landing. There's smoke coming in." And they found out what the fault was, and there was some battery system that ran a galley or something like that, which they were able to fix up. But a big engineering system very rarely goes into operation 100% without any tuning and fine adjustments as you go. But before something like that Boeing flew, it was well and truly tested on simulation and this, that, and the other, and so on. So I've got no fears that we won't be able to build a thing like this and it'll work.
Okay, so it's just what is the stumbling block then at the moment? It's just the investment needs to be there, or is there a political stumble block? What do you see like the roadmap?
Well, we have a private group in Pretoria that owns the rights to the HMR 100. It's not a government project, but we work very closely with the South African government, so they know very well what we're doing. We've got regulatory support. We've got the politicians now not opposing us. In fact, they're being supportive. Other countries, the politicians are still anti, and you've got to fight the politicians. Here, we don't have to fight the politicians. We're getting collaboration. We have a group of about 20 people working on a daily basis now on doing developments related to the reactor and so on. And we're hoping to get some good funding in. And the moment we get some good funding, we can start moving rapidly. We've got about another 100 people effectively on standby, in the sense that they're working on other projects in closely allied companies which can swing into this project rapidly. And then there's even a few hundred others from the Pebble Bed days and various others. Now, of course, in a nuclear project, I make the analogy with military weaponry, for example. Now, if you look at military weapons, 90% of a military weapon is not the weapon, so to speak. If you look at an army tank, the army tank is a big engine, a big gearbox, tracks to ride, it's armor plate, it's laser rangefinders, it's armor glass, it's this. You build that entire system, and the last thing you do is you put a gun on it. The gun is minor in comparison. Similarly with the jet aircraft, by the time you've made that jet, the last thing you do is you hang missiles on the jet and maybe put some guns on it. That's minor in comparison to all the aeronautics to actually get the platform to fly. And it's the same with the nuclear reactor. The nuclear reactor is pumps and pipes and welding and electronics and this and this and this and this. You get right to the end of building a nuclear reactor before nuclear fuel comes on board, and then it becomes something which got something radioactive. The rest is all just good quality engineering that is found all over. So that it's not as if we've got to go and find hundreds of nuclear people. There's lots of skilled individuals around that can weld and do pipe work and vacuum pumps and water pumps and electronic controls and all those things that go with it.
Okay, well, it's got sort of one more question from the audience here. They ask you, didn't Russian cities use nuclear water district heating at one stage? And I guess by extension, you could obviously use the Pebble Bed for that as well. Well, it's not a South African problem, but European issue, I guess.
I'm sure, I don't know the details of that one in the Russian case, but there certainly have been numbers of things that are done by different people under different circumstances. I know that Iceland uses a lot of heating from their geothermal heating to do things like heat roads so that the roads don't ice over and so on and so forth. So each country must have a look at its own requirements. And quite frankly, I've been pleased to see a number of African leaders in African countries saying, we've got to solve African problems with Africans for the African solution to do it our way. We can't take European problems and put them here. And that has been a snag for many years. People have made the assumption that the Europeans know what to do. And Europeans come here from European conditions and tell us, do this. There was a case some time ago where some people brought in some pumps from Germany that were absolutely waterproof, good quality pumps. They put them in the desert areas here, and in no time they broke because they weren't dustproof. The dust got in, turned into liquid sandpaper and ruined them. They said, well, we don't have dust where we come from. We have water. We said, we don't want them to be waterproof in the desert. And it's this type of thing that we've got to have the courage of our convictions, all African countries, to say, we must look at our country and determine what we want for our solution, and we do it our way. We can look at others and get advice and see what they've done, but not slavishly follow them because they're the only ones that we believe are correct. And I think they will learn a lot from us. When we develop our systems, you'll find it's applicable. I was in the US in Massachusetts, and I got invited to talk to a local municipality in Massachusetts. They were looking for small power sources that they could control directly in Massachusetts. And they said, look, your reactor looks like the answer. So there I was giving a lecture. I did it more than once in the US, and there was quite a bit of significant interest then. So, it's all over the place.
Just to follow up on that point, there's also been a move in Africa towards mini grids. You get these gated communities that are now got their own grid and stuff. And I would guess those are also ideal conditions for, small modular reactors.
Absolutely. Now that you mention that, that traditionally one talks about a grid, but of course, when you look at the earliest electricity, and in fact, one of the first in the world to get electric streetlights was Kimberley in South Africa. At about the same time as New York, there's a bit of a competition to who was first, Kimberley or New York. But when electricity started in New York, there wasn't a United States grid. There was a grid around the neighborhood. And the same for cities like London and whatever. When electricity came about, it expanded organically and incrementally. And so with a Pebble Bed reactor now, there's no reason why, like a mining community can't have a reactor that serves the reactor and some of the residential neighborhood that can be a radius of 5 kilometers, 10 kilometers.
Okay, that's very interesting, and that's something to think of, because I think there's market forces pushing in decentralized directions, and again, this thing can work of that sort. Just sort of as a final point, as we're coming in for landing here, the public, how can they find out about this project, and where can people that are curious investors, contact you or get involved?
Well, they're welcome to email me directly. It's kelvin.kemm@straticglobal.com. You can welcome to show them that address. We're busy developing a website at the moment. It exists and it should go live soon. We've also got an Australian company, by the way, that was started because of the peculiar circumstances in Australia. It's smrglobal.energy. smrglobal.energy. So that one also functions. We've got an Australian representative in Australia. And so on. Other than that, I think Google us and things will come up there. And over the next couple of months and so on, I hope that a lot more information flows out. We have got a new brochure that has just come out, a couple of brochures that explain what's going on, and we welcome people asking questions. And particularly if there's international funders, we've had some from Sweden now showing interest as well. If there's anybody who wants to know, please come and talk to us and tell us your particular requirements. And we'll only be too happy to see what we can do to come to interesting interactions.
Final question. I'm going to ask you to make a small prediction here, but when do you think we'll see the first Pebble Bed working?
Well, we've been saying 5 years. 5 years from when we start, we'll be producing electricity. And we're ready to effectively start any day now. We can start next week, so to speak, in the sense that if the money landed on the table next week, we want people to start getting more people together to start doing the next steps. We're not in the refrigerator that has to be defrosted. It's operational on a small scale, but we can go fast. And we hope that there won't be regulatory impediments, which is a lot of what impeded nuclear in the past, by the way, a lot of intentional impediments put in place by the extreme greens and so on to go along and dig laws out and procedures out to deliberately hinder progress. And we just hope that as the future comes, that there will be a lot less of that in the world, and certainly that in South Africa we don't want to see intentional impediments coming about from an anti-nuclear lobby, and we think that that will not really happen to any great degree. And that's the biggest potential delay, not a delay in the engineering.
Okay, well, I hope so, and I hope we will continue to expose the green fanatics here on this channel. But Dr. Kemm, thank you very much for your time you've given us. And I think people really need to think of this, especially in the light of Eskom's recent blackouts. Thank you very much.
Well, thank you for the opportunity of chatting to you in this very nice way, and the opportunity to explain to you what's been going on with our South African developed small modular reactor.
Okay, and to everyone else there, thank you for listening. Please subscribe and please share the information around.